Good afternoon, everyone. Am I audible, sir?
Yes.
Okay. Good afternoon. It's my pleasure to welcome our esteemed resource person, Dr. Muhammad Salim. Dr. Salim is currently a research engineer at the IPVF, France. He completed his PhD from the Institute of Advanced Materials, Spain. His research expertise lies in advanced materials and solar energy technologies. Today, he will be delivering a session on Perovskite Solar Cells, the future of solar energy. This emerging technology is transforming the renewable energy sector, and we are privileged to learn from a researcher actively contributing to this field. On behalf of Department of Applied Science and Humanities and Sripati Institute of Management Technology, I extend a warm welcome to you, sir. We are delighted to have you with us today for an inspiring session.
Okay. May going to start or
Yes.
okay.
Okay. They will join, so most
Uh,
70 participants are there.
should I need to wait more or hello?
Okay, you can start. I think 18 participants are there.
Can you see my slides or
Yes, sir.
okay, sure. Okay, good afternoon. Okay, I can start, am I right? Or you're waiting for some people or faculties or hello?
Yes, sir.
Can I start it now or like are you waiting for some people?
Oh, you can wait for some more minutes. Okay.
Oh, okay, sure. No problem.
So let's start the session.
Okay,
You may join
sure.
shortly.
Okay, sure.
Okay.
Then, okay, I'm going to start. Okay. Thank you. Good afternoon, everyone. And thank you very much for this welcoming onto the sessions. And it's a privilege to be here and to share some of the knowledge and also the science behind like what we are doing in terms of like photovoltaics, and especially in the solar energy sector. Okay, I can introduce a little bit more like what where I did my graduation and like how I eventually ended up in this field. So my name is Mohammed Salim, because I'm from Kerala, and I did my bachelor's and master's and also MPhil from University of Calicut. Then after my graduations, like I moved to NTU Singapore. Actually, I worked as a research engineer at ARIAN. So this is one of the research institute, like which they mainly focused on the energy sectors and batteries and all the renewable field. So the institute is called ARIAN, which was part of the material science and engineering department. And then afterwards, like I moved to Spain for my PhD program, where I did my PhD in Perovskite Solar Cells. Probably you might have heard about like when you are dealing with solar cells and silicon solar cells. Yeah, you also heard about this like perovskite materials. Then after my PhD graduations, like I joined like one company. It's called IPVF. So it's located in the center of like Paris. So we mainly focused on the large scale industry level fabrication of like perovskite solar cells. So mainly to combine the silicon just for the four terminal panels. So that I will talk about in the end of the my presentations. Okay, for the today's like talk, I'm gonna talk a little bit about like science and also a little bit how we can integrate a little bit from the industry point of view. And I made like a little bit scientific at the beginning, and then in the last part of my talk, I'll talk about like how we can approach towards the industry levels. So, okay, moving on to the introduction part, like why we, the importance of like energy production and also the energy sustainable energy productions. As you can see here in this figure, so this is one of the studies or like goals adopted by the United Nations. So the idea was like a sustainable development goal. So the main concept behind this goal is to have an affordable and reliable and sustainable energy for all the peoples. And as you can see from this world map, there are still plenty of countries in our like well, especially in the African sector, where many of the people they are not accessible for the electricity or like energy. The produced energy it's available in our market. So there's one concept like how we can move towards more like an affordable or reliable way. So like most of our productions are which comes from the oil and gas productions, but they are no longer part of like any sustainable or reliable methods. So the idea is like and also from the Paris Agreement from the 2016, and we found like if we are producing like or if we are meeting the energy demands, so we need to make everything from the sustainable point of view. So So we need to reduce, like, a lot of global issues related to the energy productions. So from the clean energy point of view, how we want to produce like energy. So it has been started from the 1950s, and until now, like we are mostly relying on the coal and oil productions, which produce like 55% of their modern energy demand. But from the late 1970s, like we are slowly catching up with other renewable sectors. For example, like solar, wind, hydropower, and other like biofuel methods. But there's still we are not like meeting the energy requirements from these like biorenewable sources. So there should be some paradigm shift that we need to go from like non-renewable fossil fuel to the carbon free energy sources. So as you can see, like from the renewable point of view, like sun is the best source. And when you compare like other sectors like biomass, hydro or geothermals and the tides, so we don't gain too much of like energy output from it. But the solar energy has an immense potential. So there is a capability of this electricity, or I mean the energy production from the solar. But we are still lacking in terms of like how we can get an energy production from the solars. Like I mean, there's an estimation is like if we are covering like zero point 0.4 or like 1% of the Earth surface with relatively good solar panels, so this is more than enough to meet our like energy requirement for the year. And this is actually it's quite like double or triple the energy output than the what we usually get from the oil or coal burning. So there's also like there's one action plan by like Europe and also some of the government from the US. So we need to move from like renewable parts. So how we can do it? So when we compare like photovoltaics, especially from the solar-based energies, so back in 2010, like the price levelized cost of efficiency from the photovoltaics, which actually dropped quite a lot from 2010 to 2022. So actually, it's due to innovations and research and engineering. So there's a hope there. So we can slowly like surrogate this kind of like non-renewable energy sources with renewable sources, especially with the solar PV. And this is also like global electric generation. This is an estimation from the 2022 and also 2030, like what we can achieve. So this is also part of like this Paris Global Summit. Like, so their idea is to drop their global warming or like temperature just by like 1.5 degree per annum. So and by 2022, like the out of the renewable energy productions, the from the solar PV, it was around like 1.5 gigawatt. Sorry, 1,000, around like 1,100 gigawatt productions. And by 2030, like the aim is to make like the production is like around like 5 times. And when you compare with other like renewable production, so the solar is going to be like a biggest impact in our like future energy production. So I mean, we need to move that way just to to make like more like safer and also sustainable methods. Okay, so then I talked a lot about like the solar cells. Probably if you are in an engineering or background, like I mean from our like high schools or like even in the preliminary school times, like we always talk about like what are solar cells. and what are what is the photovoltaic devices. So basically, you might have seen like this kind of panels in everywhere in the rooftops or like somewhere in the empty field, especially if you can see also in the Cochin airports. So these are like semiconductor material, especially this is how the photovoltaics works. So where you have like p-n junction diodes, and then you have like p-type material and n-type material, especially these are like from the doped systems. There it's connected with the the bottom electrodes and also load. So this when the sunlight hits the this kind of like semiconductor material, it generates charges, and especially it's called a light absorber. So this creates like electrons and phonons, electrons and holes. We call like excitons, and we need like charge carry collectors, which we use like some metal electrodes and in the end to the load. So the term photovoltaic effect is mainly the process called light to electricity. So this was the old term coined by one of the famous like French scientists. Its name is called Edmond Becquerel. It was back in 1850 something, like when he found like this photovoltaic effect when he was working in his father's laboratory when he was like 19 years old. He was quite young, and he found like he can like generate electricity by just by shining the light on like a metal surface. So that's how it started, like this photovoltaic effects, and it became the part of like a big revolution in terms of like solar cells. Okay, so ever since the history of the photovoltaic started, like we came across like various generations of photovoltaics. So this was started from like silicon solar cells. Obviously, it was from 1950s. The first silicon solar cell was started from like Bell Labs in US. So they started from like monocrystalline silicon solar cells, then eventually it became like multicrystalline. They're like quite advantageous, especially like they're high efficiency, long-term stability. But the problem is like their high fabrication cost and reduced texture. It's only like you cannot deploy everywhere, and it's like more like limited in terms of like their flexibility. And then all the time, like in 1980s or like 1990s, like it's started like second generation photovoltaics, mainly in the form of like thin films. So which comes from amorphous silicon, and also the like thin film based cadmium telluride, and then the CZTS or CIGS. These are like some of the rare earth elements. So their plus point was like they are cost effective, but there was some issues from the toxicity of the metals and also the scarcity of precursor material, especially the indium. So they are like very highly scarce. And and then later, like from 1990s, it started like the dye-sensitized solar cells. So they are like organic, small molecule organic dyes, which absorbs lights and which are eventually used in the research purpose. And there are some like labs and also some of the building research which are like with the DSCC one. But the problem was like there's an issues with the temperature. So these DSCs cannot be operated at low temperature. There's also the efficiency drop. Then eventually it comes from the organic solar cells and also quantum solar cells. And recently, like in the last 10 to 12 years, like we have been witnessing the growth and also the research development of perovskite solar cells. So this is one of the promising like third generation PV which we are phasing out. And the main advantage is like they are like very cost effective and high efficiency, which can be produced from like solution based approaches. And but the problem is like they are less stable, but they are like very also sensitive to some atmospheric conditions in terms of like moisture or temperature or other electrical bias. Okay, so this is also one of the famous charts. Like we use the people who work in the PV background. So this is like an overall growth or like the history of like what kind of like PV materials are available and what kind of like reported efficiencies are in the literature. So as you can see over here, the silicon was started quite long time ago from like 1970s. It has like long history, but the perovskite, which was like began in early 2013, and look at the efficiency phase between the silicon and solar perovskite. So silicon is like almost reached their like Shockley Gaussian limits efficiencies, which is supposed to be like 32%, but as you can see that within the short span of like time, like the perovskite is like almost like catching up with the silicon. So there's kind of like potential competitor for silicon solar cells. So for the current efficiency, we have like state of the art efficiency is like close to 27%. So there are like various types of devices also possible in terms of like single junction or multi junction. So basically we call like the tandem devices, especially if you stack like one device over another. So this we call like tandem. So you can stack the perovskite on top of like silicon, then we call like 2D tandem or 4D tandem. So then we can increase the efficiency from like, more than like 30%. So, like, yeah, we are talking a lot about like perovskites. Then, what are like perovskites? So, these are like three component systems, especially which is a crystal structure of like calcium titanate. So, this is one of the old crystal structure which was invented by this Russian scientist Perovsky and also Gustav. So they named this material like the perovskites. So this was the old crystal, and okay, I mean they used like the calcium titanate one, and for the semiconducting purpose, like what we are using, like kind of like ABX3 texture is like this. And here, this semiconductor ABX3 is like composed of like both organic and inorganic and also halide frameworks, where you can see that A is kind of like a multivalent cation, such as like organic, like formamidinium or Fa, we call like Ma, methyl ammonium, and we have also have like some of the inorganic cations like cesium and rubidium. And the B sides is like the metals like lead 2 plus, tin, and also germanium. And these the halides are which comes from the iodates and bromides and chlorides. So in the end, like you can have a multiple compositions. For example, if you have a PD, like single composition can be like a MAPBI3 or formamidinium lead iodate or cesium lead iodate. This is like completely inorganic. And you can have a combination between the halides and the different cations. So then you can have like a different compositions. Okay, so the same time, so there's also advantages with the perovskite material. Like you can tune the dimensionality of this perovskite. For example, if you have an infinite crystal structure, then you call like 3D perovskites or 3D crystal structure, and you can slice this kind of like the inorganic slabs by using like larger cations. So we call like a three-dimensional and two-dimensional mixture. So let's say if you are putting like larger spacer cations, then it became like, the n is equal to 1 and n is equal to 2. And you can have like a mixed dimensionality. So the advantage is like depending upon the dimensionality, you can have a different band gap. So that's the reason why this perovskite is not only used in the solar cells, it's also used in the applications of like lasers. It's also used in the LEDs, like also memory devices and also photo detectors. Now, even people they are using for the X-ray scintillators. So when it goes to the 1D or like zero dimensional, that's the quantum dot dimensions. So this is like quantum constrained state. They are highly good for like LED applications. So okay, come back to the three-dimensional part. So why we wanted to use this perovskite semiconductor as a solar cell material. So there are like a couple of semiconducting properties. Especially like if you want to use it for solar cell applications, and it has to be highly absorbing material. So it has high absorption coefficient, and when you compare with silicon and with perovskite, silicon behave like an indirect band gap materials. So for this perovskite is like direct band material. So like I mentioned, like when you mix like different halides and different cations, you can tune the band gap from like 1.5 eV to 2.5 electron volt. So that's why like there's a wide tunable material from perovskite. So also like low exciton binding energies. So this is mainly for like good solar cells. And in terms of like charge collection and also charge mobility, so there we have like a good carrier mobility and also diffusion length. And plus one point, it's like it can be produced from the low cost solution based process. Okay, so this is one of the primitive semiconductor. I mean, from the perovskite, it was like started from the like medium aluminum lead iodide. So probably if you heard about like DSSC, so like I mentioned earlier, like it was the one of the third generation solar cell material. So in DSSC, people they use like the organic dyes which act as an absorber. But in DSSC there were like some electrolytes there. So the same way the history of the perovskite started from the started with solid state perovskite material with the electrolyte. But the problem were like these perovskites are highly ionic in nature, so it tend to like dissolve in this kind of electrolyte. So eventually people they try to replace some of the electrolytes with some kind of like a whole transport or like some other like charge transfer material. So then eventually it became like a solid state perovskite thin films and obviously to the perovskite solar cell. So I mean, this was an first example, like the people started using with the methyl ammonium. So it was an first employed in solar cell. So when you compare the high absorption coefficient and the absorption coefficient of the methyl ammonium is quite higher than the typical crystalline silicon and also as the gallium arsenide. And you can see that this behave like very direct band offsets. And when you compare with the silicon, it's like an indirect band gap material, and this one is like very direct band gap. This usually shows like very band, like offsets here. And when compared with the silicon, this is like which was prepared very like low temperature solution based thin film deposition. So and plus this is also one word we call like Urbach energy. So this is characteristics of semiconductor material. So which explain how well ordered or if there is any defects in your material. So it showed like lower or back energy. So it means like we have a lower trap state density and also has like well ordered microstructures. Okay, so in a how we fabricate these thin films. So like I mentioned, like it comes from like solution based chemistry. So this is how we fabricate. Like we mix the the organic parts and also inorganic parts in our like desired solvents. Especially like we use some of the polar aprotic solvents like DMF or DMSO. So then the chemistry happens like from the solution chemistry to the solid state chemistry. So we for a typical small scale laboratory fabrication, we use like spin coating process. So here, oh, that's supposed to be one video here. Sorry. Um, um, what we do, like we drop cast the our perovskite solutions, and we use like a spin coater to to form like uniform thin films. Then we also use like some kind of like anti-solvent, just that is to remove the solvent in our like wet film, and also this is to start like a nucleation of like our perovskites. And it's called like we call like intermediate phase. And when you anneal this film, then you get like very brownish to black films. We call like thin film, and these are comes with very dense perovskite grains. So this is like one of the typical small scale laboratory process. Okay, so yeah, this is one of the the spin coating, how it works. We drop cast our material, then it's depending upon like our desired thickness, like we can go like high rotation per minute to the the low rotation. So we end up like very uniform like thin films. Okay, so there's also like in some issues from the the spin coating methods. So we cannot go for like a larger area. So then we need to rely on like very relatively high throughput methods. For example, like from small scale to the lab scale laboratory fabrication, we usually like use some methods like blade coating. So basically, we drop cast our like liquid films, sorry, liquid solutions. Then there will be like a blade which move from like one direction to the another, and also the same times the the surface is regulated with temperature, so which helps to remove our solvents from our like wet films, and then it forms like a very high quality thin films. So for blade coating and also the slurry coating, as actually is the same. So blade coating is more like an it's not an automated technique. Uh, when we come to like the slaughter, it's more like it's like an automated technique. So it's a big equipment when compared to the blade cord methods. So for the blade cord, you can make like a tabletop. It's like 10 centimeter to 15 centimeter small size equipment, but the slot cord is like relatively bigger. So this is one of the instrument used especially in the industries. So you can do the deposition from like 5 centimeter to 15 or like even to the 1 meter size. So this is how it usually works. Like you have an head and you have an a syringe with the ink reservoir. So based on our like commands, so it can deliver like the amount of like inks to the head, and also the motion of the either the motion of the substrate or either the motion of like the head. So depending upon our the speed of their head and also the flow rate of our ink, so we can control the thickness of the film, and also the we can control in what area, in what pattern do I need to do the deposition. So there's like a lot of like versatile between like the slow day and blade coating. So this is also comes from the solution based methods. And and also like recently in industry people they are using like the thermal evaporation. So these are with the high vacuum equipment, especially here we use like solid state perovskite powders. Let's say if I want to use like MAI and PBI too, so we use like two sources, like one is organic source and like we use like another one with inorganic source. So the idea is to use like sublime or this perovskite precursor material. Then in the end, like it will deposit and it forms like a thin film. So the main advantage is like you can get rid of a lot of like solution process from this part, but the main disadvantage is like these equipments are really highly costly because it need like very high vacuum equipment. So it's not that we can use it for like laboratory scale fabrication, but if you need like very high throughput, like very industry techniques, because if you need like very high vacuum techniques, it's going to be very expensive. So there are a lot of like merits and demerits with this kind of techniques. Okay, so this is just an comparison of like between like the perovskite and also silicon. I mean, as you always heard about like silicon solar cells, silicon solar everywhere. So you know the difference uh, between like the perovskite and also the silicon when it comes to the fabrication. I mean, Perovskite was like quite easier, which came from like one step solution process. You can do this process like in half an hour. But the but in the case of like a silicon, it usually takes very quite long and very expensive. The purification and also the instrumentation methods, which obviously it comes from the earth core silica. Then it has to be purified. Then once you purify, then you get like polycrystalline silicon. Then in industry, like they make like a silicon ingots. Then it has to go through like the shaping and also the wafers that you can see like in the panels. Then it has to go through like multiple, the high vacuum and also the equipment process to get like the final solar cells and also the module. So they when it compares to the expensive a part of the silicon with the perovskite, silicon is quite very high expensive. It's around like $2.5 per square feet, and it also need like very high thick silicon wafer. It's maybe like around like a micrometer to millimeter thick, and also like I mentioned in the earlier, like it has to be, and these are like very brittle films, so it has to be limited with some like some specific application. But the main advantage comes from the perovskite is like you can adapt anywhere, like in on the rigid or flexible or even very ultra thin, ultra thin textures. For example, even the perovskite can also work with 200 to 500 nanometer when compared to the micrometer or like millimeter scales. Okay, so then what kind of like architectures we usually use in the perovskite solar cells? So, like I mentioned in the earlier slides, like in the architecture of like silicon was like kind of like behaving like a PN junction. But in the case of like perovskites, we need to be like sandwiched between like two charge transport layers, especially we call like hole transport layer or electron transport layer. So in the old time, like when the people like started fabricating the devices, we were using like the old NIP mesoporic mesoscopic PSCs. We call like perovskite solar cells, where we have an electron transport layer in the bottom, and it's called cathodes, and then we have like a mesoporous titania. So this is uh, actually this concept is mainly come from the DSSC, because in DSSC they were using some of the mesoporous titania as like a kind of like a dye absorber, and also this can fill the pores of like titania to absorb better sunlight. So they, in the beginning stage of like perovskites, we were using like mesoporous, and then we have like perovskite, then we have all transport layer. Especially we use like organic HTL like spiro amiochars and PTA, and then we have like because we need like top electrode as like and this was in the beginning stage, and the later like it moved from like NAP planar. So we found that we have some issues with mesoporous, because it need like a very high temperature process, for example around like 500 degree Celsius annealing. So we start like get rid of like this mesoporous layer, so even it can also work with the planar titania or planar like tin oxide. Even it can also go for like zinc oxide or PCBM. These are like some of the classical electron transport material available in the market. And then the perovskite comes, then the whole transport layer comes, and also the finally the top layer as like gold or silver. So then you can also fabricate the devices in an opposite way. So that's also one of the advantages with this material. So the band offset, and also the versatility of the different perovskite with the different band gaps can be tunable between the NAP and PAN structure. So in PAN, what we do, like there's called a P type, intrinsic, N type. So this is like N type is like N type, intrinsic, P type. So here, like we sandwich perovskite between the steel and the ETL. So here it start from like whole transport layer, like especially nickel oxide or poly TPD, or like these are like some of the organic HDL which we used in the organic solar cells. So which also slightly adapted to the perovskites. And then we have like electron transport layer, like they are like PCBM or BCB or C60. So there are like advantages and also disadvantages from these kind of like architectures. So these HTLs and ETLs are like laboratory based, research purpose one, but we cannot go like we cannot use this kind of like organic materials for the very industry relevant device application. For example, the materials we use for like this pyro MTD is actually this PTA. They are like very highly expensive materials. So these 1 grams usually cost like more than €1,000. So it's not easy to scale up from like the small scale like this to the big panels like the what we see in the in our like the rooftops. So there are a lot of like challenges with the scale up of our devices. So even though these perovskite devices are working like super good, but there are also like a lot of limitation in terms of like stability, and also as well as the scale up of these materials. Okay, so like I mentioned, like there's also like challenges with the perovskite material, especially you can say like when it comes to any kind of like photovoltaic materials, we call like a golden triangle rule. So of any PV material, so first of all, it has to be efficient, and then it has to be produced from the low cost material, and also the it should be like reliable, and also as the reliable in terms of like the stability of the material. So you can see from this graph here, the efficiency and the cost are like, the efficiency of the perovskite is like quite, the similar to the what we have seen from the silicon. So it's like, so this and all the data, like now we have a efficiency of like more than 27%. So it's like it surpassed the silicon part. And when it comes to the cost, so actually this is like half of the what silicon solar cell required. So it's like, so we gain the benefit here and we gain the benefit here, but there's also a problem with the lifetime. So you even if it comes to the market in the end, like you need to validate. So it's reliability is one of the big responsible part. So you can see here the silicon solar cell, they can long last for like around 25 years, but the perovskites can hardly, long last like for more than 1 year. So there are a lot of like, the challenges we need to face here in terms of like, the stability aspects. So mainly like the stability issues comes from like various parts. Like you mentioned, like it comes from the solution-based process. So it will, especially this comes with the polycrystalline material. So we usually have like a lot of grains and so the grain boundaries. So um, and since it's coming from the ionic compounds, so these materials are highly sensitive to the moistures. So this process has to be done inside our glove box. Glove books are like, some of the control environments under like nitrogen or like argon environment. So we usually fabricate our perovskite materials in the glove box environment. Nowadays, people also start doing like doing the fabrication in the open atmosphere. So it's like it took a lot of engineering, also a lot of like research, how we can move from like from the from the glove box to the open atmosphere. Okay, so that's one of the research field. It's happening at the same time. So the issues like one of the moisture and also the oxygen. So it's these are like very weak material in terms of like absorbing moisture and also the oxygen. So once it's the moisture is in the perovskite material, it hydrates and it will dissociate the material faster. And at the same time, like under the light, what happens? Like it forms like kind of like a mixture of like halides in one part, and for example, if you have iodides and bromides in your material, so it will try to segregate, and it forms some kind of like different band gap zones. So this is also one of the issues, like when you want to deploy your final devices in a panel or like in a large area devices outside. So you need to get like very high throughput, high output. So let's say I'm placing my devices outside, and then the efficiency is like depleting over the time. So that means like there's something happening. So the material has to be robust in terms of like light and as well as the moisture and as well as the temperature. And there's also one more issue which comes from the crystal structure collapse. So when it under the temperature and as well as the strain, so what happens, like it changes the phase. So we call like polymorphic behavior. So if it's very high temperature and as well as the high strained material, so it tends to changes phase from like photoactive phase to the photoinactive delta phase. So that's also one of the drawbacks when it comes to the stability issue. So there are a lot of like future perspectives are like going on. Like so, there it comes the or gives the opportunities for the researchers and engineers, like how we can tackle this kind of issues. So which comes in terms of like material science, in terms of like physics, and also like the engineering. So how well we can, protect the grains and grain boundaries. What kind of like encapsulation material that we can use to stabilize the device, and also some of the novel charge transport materials which can be like very quite strong in terms of like high temperature and as well as the the low temperature freezing climates. Usually like the reason why I'm saying like in terms of like the stability issues, like when you want to market any kind of like solar materials, you need to show some of the reliability of the devices. So in a typical industry process, we do like kind of thermal cycling. We have to show the reliability of this material at 85 degrees Celsius, and also we need to show the same at minus 40 degrees. So it's kind of like you are cycling the temperature from like high to the low. So if anything happening to the materials or interfaces in between, so there's a bottleneck for the material. So if you can surpass this kind of like high standard IEC test, so this is one of the protocols set by the the photovoltaic community. Like if you pass these kind of things, then you're ready to deploy this kind of material in the market, and you can sell it to the the people. So this is one of the active research area in the Perovskite community, like behind this kind of like how to mitigate this kind of like a degradation pathways. Okay, so like I mentioned in the earlier part of my talk, like how we move from like small cells to the the large area cells. So there's a concept we call like the lab to fab concept. So you can see that the laboratory-based small cells, they are like mostly prepared with spin coating or like small scale laboratory based slow die coatings. So there are a lot of like phases for the devices. So they call a pre-industrial solar cells. We call like modules or like mini modules. Then you have like industrial solar panels. We these are like in the TRL. They are called technology readiness levels. So the categories they are like around TRL 9 or 10. So which comes in the size of like like 1 meter over like 2 meter sizes. So there are a lot of challenges there, like for the perovskite to be, like transferred from like a lab to the fab concepts. So like I mentioned, like from the small scale, so we usually use like spin coating. Then there are a lot of like disadvantages. So one is this is like limited with the device active area. So you get very good efficiency from like less than like 1 centimeter square. There's a problem with the high material wastage. So even if you are spin coatings, you are wastage in a lot of like 90, more than like 90% of the solutions or like material that you are trying to deposit. And you cannot scale up this like more than 5 centimeters. So this it creates like a lot of inhomogeneity issues on the large area. So this is called unfeasible for the commercialization goals. So there it comes to the the platform of like high throughput methods, especially the slow die coatings or like inkjet printing or like I mentioned the thermal evaporation. So the advantage is like you can go like large area devices more than 100 cm square. Now we can go like more than like 1 meter over like 1 meter size with the solar coatings. So the main advantage is like it has like less material wastage, and you can control the uniformity of the material over like different sizes, different substrate. So that's called you can have like versatility towards like different substrate size and nature. So it's we can integrate this kind of like high throughput techniques or like methods in the inert atmosphere. You can also put like in the dry or open air fabrications. Okay, so um, in a nutshell, like what we do here, like so, like I mentioned, we earlier we used to start with the NIP based devices. That's the N-type, intrinsic, and P-type material. So, in a scale-up process, this is how we usually do. Like we need like transferring conducting oxide. So we use like FTOs, and then for a large area modules, like we need to make a different from like one cells to the different. So we use um, like the scribing process. So before that, like we also need like the electron transfer layer. We mainly use like the thin oxide, so that we grow by like a chemical bath deposition on like 10 by 10 substrate. Even also we can grow like more than like 15 by 15 or like 20 by 20. But there's also a lot of limitations with the CBD process of like thin oxide. And then we move to the, once we have the ETL layer, then we move to the perovskites, which comes from the solution of like, the perovskite material in like polar solvents, polar protic solvents. And then we use like air knives to remove the solvents, and then annealing, we get like very good quality and shiny perovskite thin films. Then afterwards, like we use the whole transport layer, especially this is HDL as like a spirometer, and then and the later, like we need to scribe the this material from the P2 side, and finally, like we go for like the metallizations, like back contact and deposition. So basically, um, the modules is actually the scale-up version of individual small cells. So um, you can have one device in small area, like in 1 centimeter. But what happens if you go from like 1 centimeter to like 10 centimeter? There are a lot of issues. So you cannot directly scale up like that. So the issues comes from the sheet resistance, and also the conductivity of the TCO that we use. So in order to avoid into the big one areas, we usually use to describe like small cells. Then we series interconnect these devices. So for example, yeah, this is one, this I was mentioning. So let's suppose if you have like different cells from like 1 centimeter square, like 1, 2, or 3 device. So let's say if you want to scale up to the large area, so we usually do like a series interconnection of subcells. So which comes from like P1 to P2 to P3. So this area we call like a dead area, and also this is the main active area where all the charges transfers. So it goes all the way like this. So that is how we do this kind of like a P1, P2, P3 scribing in industry modules. So in a series fashion. So we can also design these modules in the parallel one, but there are a lot of engineering and also the device physics need behind this. So here the main idea is like it's also depending upon our like goal. Like if you need like very high voltage modules from your devices, so it has to be connected in a series. And if you need like the high current devices, like sometimes we connect in the parallel fashion. So it's a kind of like a where you engineering meets like device physics. So we started demonstrating like from small cells to the large area, like in this kind of like a series devices. And obviously our goal is to make like the large area of like into 13 to 60. So once you have like 13 to 60 sub modules, what we do, like we connect everything in series or in parallel according to our like voltage requirements, and then we make like the panels. Okay, so like yeah, this kind of thing. This is one of the example of like silicon, how they design, how they do the electrical circuits. the same way you can also do with the perovskites. So there are a lot of like companies in China. They already established and also they demonstrated this kind of like high TRL panels. They are like in the size of like 1 meter over 2 meter. So the science is progressing because the Chinese, I mean, this Chinese R&D is like quite ahead than us, like because what they are doing, well, sorry, what we are doing now is like they already started like quite far long ago. Like they started like this process like 4 or 5 years ago. So now we are so far ahead, and they need a lot of like science, engineering, and also device ideas, like how you wanna integrate this kind of like material into the real panels. Okay, so okay, and what we do like also in the same time, like I mentioned, like this comes from like a solution-based method. So we wanted to make our process like more sustainable. So we do a lot of like research, and also we have like a lot of like material science engineers, and also we have a lot of like device physics teams to work behind, and we do a lot of optimization in terms of like a chemistry point of view by analyzing suitable solvents, and also we do a lot of like ink rheology, like how we can use the this kind of like solvent mixture for the slotted coating, especially you need to adjust the viscosity of the ink and also the ink stability, and how faster you can get rid of the solvents from your wet thin film. So there are a lot of chemistry aspects related to it, and not only the solvents matters. Like you also need a lot of like chemical additives to improve the quality of the thin film, because we wanted some point of time we wanted to expose this kind of material in the air for the post processing. So the material has to be very robust, and also should be long lasting. So, and also you need some kind of like additives for the process, optimized process for like a very large area thin films. For example, like we also use a lot of like characterization tools, like whether we are having issues in the thin films. For example, you can see this kind of like patterns, processing defects or dust. So this is like some way of like like in situ analysis, like where we wanted to target, like what kind of like defect points are what we are observing during the slow day coatings. So it's a kind of a mix between the chemistry and device and also the process alignment. Okay. Okay. With this, coming to my conclusion, like what I have presented here, like you can see, like I've discussed a lot about like energy demands and what kind of sustainable energy production that we needed. So, and we discussed a lot about like the perovskite and perovskite material. So it's one of the wonder material in the last decades when it compared to the other semiconductor materials. But there are apart from the solar energy applications, these are also widely used, for example, in LED sensors, and also memory devices, and also there's some space application now people are doing. So it's like it's actually like really wonderful. I mean, some people, especially in the academic field, those who are working on basic research or like material scientists, it's a best platform to do, like to play with it and to know like its properties and material. But it's also one of the opportunities for the PV people, those who work on like this kind of like solar devices. So there's also like challenges in terms of stability. So there are a lot of like plenty of room to improve. So there we have an opportunity for the like a lot of students, material science, and these engineers, and also the device physics, how we can tackle this kind of stability issues. And obviously, we don't want to limit our research into the small cells. So there's a concept of like lab to fab like process is going on. So it's an hot topic, and also sort of one of the ongoing, like very interesting science. Okay, with this, like I'm concluding, and I hope I can convince you a lot of things from like what's Perovskite and what we are working on. And okay, thank you for your attention. And like, if you have any questions, like please let me know.
Okay, participants, if you may have some questions regarding this session, you can ask now.
Sir, I have one question.
Sure.
Sir, what is the current efficiency of solar cells?
You mean the one with the perovskite?
Yes, yes.
Yeah, it's around like the state of the art is now around like 27%, but these are on like small area like 0.09 or zero point 0.1 cm square. So it's like I was mentioning, like there is a lot of the efficiency gap between small cells to the large area devices. So we lose like a lot of efficiency when you scale up from like small cells to the larger one. So if we get like let's say 20% efficiency, like what we get from like silicon panels, the same as for like perovskite. So it can be a good part. So it can be the substitute for the silicon maybe in the future.
Thank you, sir. Thank you.
Okay.
Any more questions?
Okay, it seems there are no questions.
Sure.
Sir,
Thank you.
could you please stop the sharing screen? Okay, thank you, Dr. Salim, for wrapping up our final technical session on such a high note. Your presentation perfectly summarized the essence of modern extension engineering education, leaving us with a great ideas to implement in our own classrooms. We are truly appreciate your time and expertise, sir.
Thank you.
Okay. With this, we conclude our final session of the FDP and will now move directly into our formal valedictory function. Gratitude is the finest blossom which springs from the soul. No program is complete without acknowledging the hands, minds, and hearts that work tirelessly behind the scenes to make it a grand success. To deliver the formal vote of thanks, I now have the distinct honor and privilege of inviting our pillar of support and visionary leader, our head of the department, Dr. Praveen P. Nambishan. So please.
Am I audible?
Sir, yes.
Okay. Have a pleasant evening, participants. It is been immense pleasure for me to propose the vote of thanks officially. It was a great journey from past 6 days, Monday to Saturday, 12 sessions, and a lot of knowledge which we spread off. And we got enough participants and they were attending with a keen interest. And first of all, I would like to thank our Sripati Institute of Management and Technology for giving the constant support, and Dr. S.P. Subramanian, principal of our college, various head of departments, teaching and non-teaching staffs, and my dear participants. Moreover, I would like to thank the co-coordinators, Ms. Soumya and Ms. Mayashri, for conducting this event in a successful way. We would like to have the certificate presentation ceremony as well now. So hopeful, like it will be an enthusiastic journey for your life in the future as well. So we'll be proceeding to that. Please. Okay. So I'll just read the name once. Miss Nitya, Miss Manjula T, Lakshmi S, Surya, Dr. Surya S, Mrs. Amisha JS, Miss Leena Mohan, Mr. Basil Joy, Dr. Sindhu C, Dr. Shiva K, Dr. Vinod K, Miss Sukanya SK, Mrs. Joshita PN, Miss Shimna M, Miss Archana R, Miss Anupa VK, Miss Aishwarya Prakashan, Miss Manchurani Matthew, Mrs. Vandana M, Mrs. Shweta, Mrs. Arya, Mrs. Ashwati PJ, Mrs. Suja Devi, Mr. Sajeev K. Jose, Ms. Ashwati, Ms. P. Manjula Unni, Mrs. Princey U, Mr. Mahesh S, Dr. Smita TG, Mrs. Nitya M, Mrs. Anju S, Mrs. Lakshmi G. Ashok, Mrs. Asif Rahman, Ms. Suja C.K., Mrs. Danya R., Dr. Bharadiraj De, Dr. Prasanna G. Vaga, Dr. Kirti M. Simon, Ms. Winnie Wilson, Mrs. Nita George, Mrs. Michelle K.N., Mrs. Pramodamol P., Mrs. Savitri K.S., Ms. Anju Nair, Ms. Diana K., Ms. Aparna V.S., Mrs. Aparna M., Ms. Rashmi S., Mrs. Ramya P., Ms. Shamsina T.S., Mrs. Saina Muhammad, Ms. Binita S., Dr. Geedu R., Dr. Santosh M.V., Dr. Nidhi, Ms. Apsara Pidambar, Dr. Monica, Dr. Ambika Gandhi, Ms. Sabira M., Ms. Salma Najib, Mrs. Sushma M., Mrs. Safini E.M., Ms. Aditya V., Ms. Anjana A., Ms. Shruti S., Mrs. Sujitra Rajit, Mr. Muhammad Moizuddin, Mrs. M. Selvalakshmi, Ms. Nasla Kamaru, Dr. Saumya S., Mrs. Jayashree A., Dr. Elsa P.J., Ms. Shamsira M., Mrs. Miduna P.M., Mrs. Sarita M., Mrs. Misal, Mrs. Fanisha Parveen, Ms. Kartika K. So thank you all. Thank you for the participation. And have a great future ahead. Thank you so much.
Thank you, sir.